Hey everyone, today the lesson is identifying rational and irrational numbers. And before we talk about which numbers are rational and irrational, I want to do a little background of number sets in general and different decimal types to give you some background so we have something to talk about when we talk about rational numbers and irrational numbers. So, rational numbers, if you were in class watching this, much of this will be covered up. So let's just focus on one at a time. Counting or natural numbers. Counting or natural numbers is when you're 1 year old, maybe 2, what you started counting with. You didn't start with 0, you started with 1. So it's 1, 2, 3. Eventually you learned to count up all the way to 10 and 50 and 100. So all of those numbers are counting numbers. You got a little bit older, and soon, especially if you had older siblings, you learned the idea of having nothing. She stole my cookie. I have no cookies. She stole my piece of candy. I had no candies. So then we added 0 to our idea of numbers. So 0, 1, 2, 3, 4 are all whole numbers. So with whole numbers, it includes all counting numbers, and what's new is 0. Next comes integers. Integers are all whole numbers and their opposites. So like ... So -4, -3, -2, -1, 0, 1, 2, 3, ... So all whole numbers and their opposites. So what's new are the negative numbers, but notice that there are still no parts. So we don't have any 0.5s or 1/3. It's just the whole numbers and their opposites. The next number set is rational numbers. Rational numbers are still all of the integers, so it's all of these, all whole numbers and their opposites, but now we include the parts. So it might be -3.5 or -10/5 or 5 or -3.2. So it's all whole numbers and their opposites plus the parts that fit on a real number line. We're going to be talking about this word ratio. Ratio, you know, is like the A over B. So it looks like a fraction. So that's a ratio. Irrational numbers are numbers that are not ratios. Not ratios. And I'll show you what I mean by that in a minute. And all of this make up the real number set. And there is, believe it or not, an imaginary number set. So not a real number, but an imaginary number. But we're not going to be talking about that today. I also want to talk about different types of decimals before we get into actual problems. So repeating decimals are decimals that repeat. For example, 0.3333, etc., etc., etc. Or we could use bar notation, 0.3 or 0.1232323, where the 2, 3 repeats, or bar notation 1.23, where you only put the bar over the 2 and 3. So repeating decimals. Terminating decimals. To terminate means to stop. So 0.5 is an example of a terminating decimal. 0.1234 is an example of a terminating decimal. As long as it stops eventually, it's a terminating decimal. And then there's the non-repeating, non-terminating. 0.321486, etc. Oh, that was a 2. 6, etc., etc., etc. So it doesn't repeat, but it doesn't stop. It could also be 0.1, 0.11, 0.111, 0.1111, etc., etc., etc. So here there's a pattern, but it doesn't repeat. The same numbers are not repeating. We can't use bar notation. So there's a pattern, but it's not a repeating pattern. Those are non-repeating, non-terminating. So let's get into what makes a rational number and what makes an irrational number. So I have it really basic for you right here that you can go back into your notes and look when you need to. A rational number is a perfect square. So remember what a perfect square is. It is a number that times itself equals this. So 4 is a perfect square because it's 2 times 2. 9 is a perfect square. 25 is a perfect square. So if we took the square root of those, it would be a rational number because the square root of 9 is 3. The square root of 25 is 5. A rational number is a terminating decimal also. That means it ends. So 0.5 is a terminating decimal. It's a rational number. Repeating decimals are also rational numbers. So 0.3 repeating is a rational number. And the reason all three of these are rational numbers is because the mathematical definition of a rational number is it can be expressed as a ratio. Now again, a ratio is something that looks like a fraction. So it can be an improper fraction, but something that looks like a fraction is a ratio. And so if you have the square root of 25, that's 5, which is the same thing as 5 over 1. The square, 0.5, you know is the same thing as 1/2. It can be expressed as a ratio. 0.3 repeating, so repeating decimals can also be turned into fractions, and we're going to be learning that tomorrow. 0.3 repeating is a common one, 1/3. So each one of these can be expressed as a ratio, which is what makes rational, rational. Irrational numbers cannot be expressed as a ratio. So that includes the square root of non-perfect squares, like the square root of 3. You can't find a number that multiplied by itself gets you 3. 1 times 3 equals 3, but these aren't the same numbers. These two have to be the same for it to be a perfect square. So if you take the square root of a non-perfect square, what you're going to get is a non-terminating, non-repeating decimal. Non-terminating, non-repeating decimal. And again, you might have a pattern, but it's not a repeating pattern. So you might have a pattern, but not a repeating pattern. So your rule of thumb is, if you have a non-perfect square or a non-terminating, non-repeating decimal, it's irrational. If you have any of these types or a fraction, it is rational. The most common famous irrational number there is pi. I am going to hopefully remember to put a link onto the Blackboard site of a game that will let you practice just telling whether something is rational or not rational. So that's the first part. But to be proficient in this learning target, you have to be able to tell why. You have to be able to justify your answer by naming what kind of decimal it is, or by telling why it is either rational or irrational. So you could say, it is rational because it is a ratio. It is irrational because it is a non-perfect square. But today we're just going to be practicing what kind of decimal it is, so they're already in decimal form, and then we'll add in our other ones for the next lesson. So the first thing you need to decide is what kind of decimal this is. So look back at your notes, and anytime you're watching a video, I would love for you to pause the video and answer it before going on so you can see if you kind of like your own formative. How well are you understanding this? Okay, so this decimal ends. Therefore, it is a terminating decimal, which means terminating decimals are rational. This next one, this dot, dot, dot means that it goes on and on and on and on and on. So here, it is a repeating decimal because the 3's are repeating. We could put it like that. So it's a repeating decimal, which means it's rational. Because I've already told you, repeating decimals can be put in fraction form, and we'll be learning how to do that tomorrow. So rational ratio. And the last one, 8.9860, etc., etc., etc. I don't see a pattern here. Definitely don't see a repeating pattern here. So this type of decimal is non-repeating, non-terminating. So this one is irrational. I suggest you do a few more examples using the game link just to get whether they're rational or irrational before continuing to your assignment. Thanks, guys.